So today we're transitioning more away from tutorial lectures to some presentations on recent research applications of quantum Monte Carlo and also some new techniques that are being developed. And I hope you'll be able to see the connections between the techniques that are being developed and what we've learned from the applications. So I'd like to start with 25-minute or so talk on some recent solid-state applications done with the quantum Monte Carlo groups at Oak Ridge National Lab. So I've used our sort of standard boilerplate here. And I was originally going to talk only about applications on transition metal oxides. A lot of people have been asking about some quite ambitious problems, and so I'm going to show some work on cuprates and give pointers to some of the defect work that we've been doing. But I think it's also important to show a much more straightforward calculation. I'm going to show some work on layered nanomaterials. This is the work we did on graphite and lithium intercalation on graphite, because this is a much more straightforward calculation and is really a direct application of the methods that we've all followed in the labs this week with standard shooter potentials, and that works very well, and we're able to learn a lot about that system without really having to worry very much about the techniques. So let me start with some acknowledgements. And actually one reason I'm going to feature this section, a selection of materials, is that really the people who did the work, Katerina Foyevsova, Ryan Santana, and Panchapeka Sanganesh, in most cases this was actually their first QMC calculation. So Katerina and Ryan had backgrounds in DFT and quantum chemistry, started their postdoc and got on with the research results that I'm going to be showing. Ganesh is now staff at Oak Ridge National Lab, but did the work on graphite. And Jaron Krogel, who was here teaching the labs earlier this week, Fernando Rabarido, and of course myself, were supervising the work. This work was run on Titan at Oak Ridge, and the Department of Energy sponsored the work. So what I want to do is really illustrate what's possible currently, give some hint about and also give some hint about how this actually work could be extended or improved in the future. So because I'm co-author on the work, I can be slightly critical without setting off a war. The PDF of this talk is online, listed on the schedule, and I've tried to make the links to the papers hot links so you can get there directly, because I also know that a few of the graphs towards the end of the talk are often quite difficult to read under projection. So I'm going to talk about a calculation of the magnetic exchange coupling in cuprates superconductors. I'm not going to talk about the calculations that we've done for defects in zinc oxide and really the development of defect calculations in quantum Monte Carlo, but I'll be happy to talk about that later. This is actually an area where the method is extremely useful because it is very difficult to obtain thermodynamic information about defects in materials from experiment. And so some additional corroboration or validation is really appreciated. And of course, particularly in metal oxides, you can cross metal insulator transitions, for example, so there can be big changes in the behavior of the material. So instead of talking about defects, I'm going to talk about graphite binding and lithium intercalation. Okay, so first topic, cuprate superconductors. Of course, these are very famous for many reasons. And of course, they're also famous because we don't have good predictive methods for these materials when all the atoms are included. We have simplified models that capture a lot of the physics, but we can't yet link those to materials. And of course, it's worth noting that even the parent compounds of these materials are Mott insulators, and those are very challenging to compute accurately and predictively in electronic structure methods. So of course, we have zero temperature quantum Monte Carlo. So what are we trying to do here, as many of the properties of these materials are interesting at finite temperature? Well, in addition to getting the ground state right, of course, what one would think of doing in the longer term is connecting with all the wonderful model Hamiltonian work that's being done in this area. That's where finite temperatures are accessible, and of course, we'll find out in future how true this is, but given the importance of doping of these materials, and the role of disorderliness materials, it seems actually quite possible that if one wanted to predict the properties of these materials, you will need some atomistic information in your model. So we obviously need an accurate method that includes atoms. Of course, the prototype cuprate superconductor is lanthanum copper oxide, often shortened to La214, 40K transition temperature. And it has the generic phase diagrams. This is temperature, and this is doping, where it's an antiferromagnetic insulator at no doping, and this is actually where we're going to be calculating, right in this corner. And then when you dope holes in, there's a superconducting region, and at sort of 15% or so, you have the highest transition temperature. So this is, and then of course there's a large class of superconductors. There's dozens and dozens of these materials. So we would like to do some QMC calculations on these. We started this work a few years ago, and so of course our first concern actually was about Schroeder potentials. So there weren't any published calculations on copper. There were a few calculations on 3D elements that had been done. So this was obviously an area of concern. Okay, so what did we do? We followed the Schroeder potential testing sort of regimen as has been explained in the labs. One extra thing that we did that I think is worth mentioning is we had to start by asking ourselves what's the minimum number of electrons we need in the valence? And one can do actually a fairly straightforward test here to get a hint. And that is we tried different calculations in DFT comparing to all electron results and sort of saw when we actually obtained a good reproduction of the density of states. Now, this was in DFT, of course, but we know it's not going to be any easier in the full many-body calculation. So in this case, we found out that argon core copper potentials didn't seem to be close enough in reproducing the density of states, and we ended up choosing neon core potentials, which have 19 valence electrons. So we're just looking for the density of states to sort of stabilize as the number of electrons are added. So I should stress that when we use a potential that's defined for QMC, we're not trying to reproduce the LDA band structure for example. So that gave us a starting point. And then we did tests of ionization potentials, electron affinities, and of course the dimer, which turns out to be very revealing. So of course we knew we had to be very careful here, and we ended up making a very hard potential with 19 valence electrons in it. And so by hard, that means we need a large number of plane waves to converge it. We've got deep potential or fine wiggles in the wave function that need to be resolved. So we're running at about 500 Rydbergs in plane waves, and this is a factor 4 or so larger than what one might be using if we were just generating a potential for DFT in LDA, PBE, or so on, for example. So this is quite hard. This uses a lot of memory, both in the underlying DFT calculation for the trial wave function, but also in the splines, which we've heard about. But as to stress, of course, this only affects the memory usage. It's actually not more costly to evaluate in the quantum Monte Carlo because we're evaluating in real space. But this wave function is going to have to fit in memory. And we're very heartened to see that when we ran the copper oxygen dimer with this 19 electron potential, that's this dark curve here, we were able to get within 0.01 angstrom of experiment with the standard single determinant wave function. So we thought that was close enough. We've also had calculations of binding energies and other standard properties. We, of course, tried to make a softer potential than the 500 Rydbergs one, but really we weren't successful. So we sort of realized in this case, okay, we have to pay. So then how do we do our QMC calculations? Well, as I mentioned earlier, there are, of course, many copper oxide superconductors and many parent compounds, and we really didn't want to start doing lanthanum copper oxide, because that would mean we'd have to make lanthanum. So we decided to start with one of the parent materials, which is calcium copper oxide, because calcium being much easier to deal with Schroeder potential-wise, and only copper being our real worry. So this followed the standard recipes, and we're going to calculate the exchange coupling in a very simple-minded way, which is looking at the energy differences between ferromagnetic and anti-ferromagnetic solutions when we built those trial wave functions in the DFT. So we set up a wave function with spins this way, another one this way, and through the energy difference, we can extract the exchange coupling. One thing that we also did is we did a very simple optimization of the nodal surfaces. And this is something that's quite standard in the field now, which is one uses a DFT plus U. One can also use hybrids. But now we're just using these as a simple parametric scan to generate different nodal surfaces. So we run with U of 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're going to feed those into the diffusion Monte Carlo. And because it's a variational method, the lowest energy that we get is the best wave function. And so this lets us make changes to the nodal surface, which we wouldn't get if we were just optimizing a Jastrow, for example, because this, by construction, does not change the nodal surface. And of course, and this variational property is going to be very useful when comparing against experiment, it turns out. So just a note on a few technical points. So we have a point, this may be too small, actually. I don't know, 0.05 atomic unit time step. We use up to a 221 unit cell, so this is just under 500 electrons. We did a finite size test using a smaller supercell, and the calculated exchange coupling didn't vary very much. So we are somewhat converged. And just a note on the cost of this, for this supercell, it was about 2 million hours for the statistical error bars that I'm going to show. So that is not cheap, but that's sort of the size that one can get on a large supercomputer allocation these days, and will of course get easier and easier. So what about the results? So I'm going to spend a little while talking through this. So this is the structure that we're running, and up here, in this top part of the plot, I'm showing energies for the ferromagnetic calculations and the anti-ferromagnetic calculations in the quantum Monte Carlo. And this U is our parameter scan if we're doing for the quantum Monte Carlo calculations at least. And at the bottom here, I've got the exchange coupling. And these yellow bars indicate a couple of experiments and the uncertainty associated with them. And so by taking the difference between these energies, we get these calculated exchange couplings. So we know that a lower energy in the DMC is a better result because it's variational. And we see we're getting the lowest energies when U is 1 or 2, so somewhere around here. And so when we take these numbers and compute the exchange couplings, we end up with these black points. And very happily, these are well within range of the experimental values. So this is a really nice result. So the best variational wave function coming from the quantum Monte Carlo has the best agreement with experiment. So the less good wave functions actually have worse agreement. It's a little bit mean to keep hammering DFT plus U, but let's do that for a moment. So this is not a predictive theory for this method because the exchange coupling is completely tunable as a function of U. So you would need to use perturbation theory or something like that to get hold of a U. You shouldn't deceive yourself that you're making a prediction in that method. So that was really heartening. So this is really an encouraging result for these copper oxides, and actually this has been extended to other cuprates now, so the same sort of scheme continues to work. Right? But what are some of the issues that we face doing this? Well, we have to be able to construct good trial wave functions, and that means the magnetic ground state has to be stabilized in wherever getting the trial wave function from. And so we're really quite limited in what we can do there in the DFT or the Hartree-Fock that we're using to generate a trial wave function. And so clearly this is a case where fully optimizing the wave functions in the quantum Monte Carlo would be desirable, because we want to really use the method where other theories are unreliable. So we can't rely on them too much, very simply logically. This is still quite a costly calculation. We would like to go on and look at doping of these materials, clearly. But that's actually going to be more expensive. We're going to need larger cells to do that at a realistic doping. So the parent materials are accessible. Doping is much more expensive these days. One weakness, of course, of this study is that we only got one number. And perhaps we were just lucky. So really, we need to have other properties having good agreement with other experiment in order to convince ourselves and the community that we're getting the right answer for the right reason. And of course, it's desirable to extract more information, much like David was saying, get away from just having energies to inform, to learn more about the materials. And for example, what we might like to do is help constrain the finite temperature lattice models. And for example, some work on this has been done by Lucas Wagner, who's here, looking at density matrices and excitation energies to constrain finite temperature models. And that's really the way forward to learn more about these materials, I think, getting away from just a single total energy or simple properties such as that. Now, we did follow up looking at some parent compounds of other simple oxides that will turn up in other cuprate materials. So again, for calcium, strontium, barium, yttrium, and lanthanum, we looked at ionization potentials, electron affinities of pseudoatoms, and then we checked the lattice properties. So here we have scans of energy against volume. And then when we compare things like the cohesive energy and the lattice constant, we actually find a very happy story. So here, this is the error in the binding energy, and diffusion Monte Carlo is red, so more red is worse, because this is the error against the best available experiment. And we see that here in this case, diffusion Monte Carlo is by far the most accurate, even with our current wave functions. And even hybrids, for example, are in purple, have an error of several percent for these materials. So just using hybrid DFT doesn't magically reduce the errors even down to 1% in this case, which is, of course, unfortunate because it's a cheaper method. When we look at the errors in lattice constant, we again see nice results from the single determinant fixed node diffusion Monte Carlo. And we do see an interesting trend here. Right? We see a growth in the error as we move to the heavier elements that are included. Now, of course, what we don't know at this point is where that error is coming from. We have some thoughts. Clearly, it's going to be some contribution of nodal surface and shooter potential errors, but at this stage, we don't know. So that's actually a research topic. Can one make a better shooter potential with smaller errors here? Or do we really need to optimize the orbitals in the trial wave function, or use a more sophisticated trial wave function, such as backflow, to reduce this error? So some comments. So with the current technology, yes, we can be successful. We do have to be very careful with shooter potentials of heavy elements. And one thing I'd point out here is, of course, we are relying very heavily on known structures. These are quite high symmetry systems, and the structures are very well known. Well done by X-ray. Lots and lots of studies have been done over decades now. Whereas if we were doing a new nanomaterial, much less might be known about the structure. And so we'd have to at least do some tests of different structures in that case. So clearly forces would be desirable. And I pointed out the cost here. So the parent materials are accessible, but if one wants to start looking at the roles of doping, that's going to be much more challenging. Any quick questions on the cuprates before I switch topics? Okay, I'll keep going then. So of course, I'm switching topics now to the world of layered materials and graphite. And I'm sure everyone in this room has heard about all the interest in layered materials. They continue to grow, both in terms of fundamental properties and also in terms of applications. There's a very nice review on potentials of heterostructures of layered materials by Guyman Grigorieva. It's been well cited, and there's a lot of labs working on different combinations of materials now for new light emitters, for example, and new electronics. Of course, we know on the theory side that these are van der Waals-bound materials, and we know that's problematic for many methods. However, there's been a lot of work on van der Waals in quantum Monte Carlo, and it's now been well established that really the standard methods, as we followed in the lab, work very, very well. Fundamentally, it's helpful that we have the full unapproximated Coulomb interaction, and I think David has a paper showing that the Jester actually essentially picks up van der Waals quite naturally. So there's fundamental reasons why we should be doing a good job of van der Waals materials. There's a nice review of this by Dubetsky and Mitash in Chemical Reviews, which also actually goes into solid state calculations as well, not only molecular calculations where they've done a lot of work. So I'm going to talk a little bit about our work on graphite. Started a couple of years ago, and our motivation for this is that we wanted to model lithium intercalation of carbons for some lithium-ion battery modeling related work. We wanted to get to a large-scale simulation, and the question is what properties should be reproduced? Because experimentally, we only have limited access to data. So one thing that's known is that if we look at the voltage versus a reference lithium metal electrode against the amount of lithium in graphite, experimentally, there's a staging effect where we get a stair step as the lithium orders into different layers in the graphite. And if one does PBE-DFT, I think the standard DFT is, you're off by, you don't get the full staging, and you're off by couple of tenths of an electron volt in this region. And this is quite hard to improve upon in a non-empirical way. Now, a couple of tenths may not sound like much, but if you're a battery manufacturer or trying to come up with new materials, you would like to be much better than that, because that percentage improvement would be very well worthwhile. I'll note that the other side of the battery, which is typically a metal oxide, such as lithium cobaltate or lithium nickelate, is also quite problematic. So this is a review article by Gerd Seder, and we see that if you empirically pick a U in DFT, you can get within a couple of tenths. You then do a hybrid, and actually results get worse because you've used a non-empirical method. And so the question is, what are you going to do? In our case, for graphite, of course, we're going to do quantum Monte Carlo and get some fundamental reference data. So, of course, it's not always necessary to simulate the full complexity of the system to learn important information about its properties and the underlying principles that are controlling it. So we actually did a series of model calculations. And instead of looking at A-B stacked graphite, so of course graphite is made of layered planes of graphene, hexagonal planes, and they have an orientation with respect to each other. Instead of looking at AB, which is the ground state where a lot of work has been done, we thought to look at AA stacked graphite. Now this is higher symmetry, so it's going to be easier for us in the quantum Monte Carlo and to learn what's going on. We won't have to worry about the geometry, for example. But also in the back of our minds, we knew that the people who are developing DFT functionals for the system had probably not done so many checks on AA. Whereas if you're developing a van der Waals functional for graphite, for example, you're certainly going to check AB, and if your functional is bad, you're not going to publish. So we thought this might be a better way of sorting some of the developments. So we're going to do a very simple calculation. We're going to have aligned planes, and we're going to vary the separation. And then later on, we're going to add some lithium atoms in the middle and move them around, look at the diffusion barriers, and look at the binding energies. So really, this is a very simple calculation. I think the computational methodology shouldn't surprise anybody here. I think I've touched on this. We also looked at various DFTs, so local DFT. There's a DFT-D2 is Grimmer's method, which is sort of like a Leonard-Jones style addition, which is adding a term to the Hamiltonian based on the polarizability of the atom. This is, of course, motivated by electrostatics and is, of course, very cheap to incorporate and hence popular. And then, of course, there are more sophisticated schemes coming along, including self-consistent functionals. I need to speed up slightly here. So let me move to probably the main result. And this would be easily reproduced, I think, by anyone in this room following the lab recipe. So this doesn't project very well, but it'll be more visible on the PDF. So these are results for AA graphite. So what I'm plotting here is the binding energy per atom against a lattice spacing. So obviously the minimum gives us the ground state separation. So our QMC results are this black curve, and this is actually our data, and we have our error bars here, which are pretty small. And this compares with experiment, which is this vertical line here. I was only able to find one experiment done on epi layers of this material, so there's no prediction of no measurement of the binding energy. We'd like to see one. And we see that our minimum is actually very close to the experimental minimum, so we're within 0.1 of experiment, just using the standard wave functions. And now, of course, we can compare against other methods. I should also note that earlier, there was a calculation done by Leonardo Spanu, Giulia Gali, and other workers on AB graphite, and we like their calculation. And that's hard to spot here, but there's a gray curve with larger error bars. And appropriately, this is smaller in separation and at a lower energy. So so the physics is coming out correctly here. So AB is the ground state, and AA is slightly higher, but not so much higher in energy. And we see various trends in the DFTs. The self-consistent functionals are really behaving best, whereas the non-self-consistent version of Tikhotenko-Scheffler is actually significantly overbinding the system. So that was a surprise. They know about that, and they fixed this behavior in the self-consistent version. We also looked at diffusion barriers, and I want to move on quickly here. So what we're doing is dragging lithium between the centers of Seitz, and we can look at energy barriers. Here, because of the symmetry, we know exactly what the transition state should be. And one interesting thing actually we found is that simple DFTs are actually very accurate, whereas some of the other schemes actually considerably worsen the results. So some of the attempts people were doing to improve their predictions, adding van der Waals methods, were actually worsening their data. And so this is actually something we wanted to understand. I'm going to skip on a little bit here. We've done this for different paths. We also looked at the lithium binding energy. Here, this is a much more expensive calculation. But what I want to quickly get to is some of the understanding that we extracted from this. So we found that schemes that were working just from using the density from local DFT were less accurate than the self-consistent functionals. So what's going on there? And by looking at how the charge density was rearranged in the quantum Monte Carlo, there's actually a very simple explanation. So this is a charge density difference where red is increased charge and blue is decreased. So our lithium is this big green atom here, and we see it's giving its charge to the lattice. Right? That's obviously what happens when it's bound to the material. And so obviously the charge density here has changed, and so that's something that's important to collect. And also it also means that the polarizability of this lithium atom is now going to be different because there's no charge there for the polarization. So if you have a scheme that depends on the polarizability of the lithium atom, it's important to reparameterize it based on the actual charge that's there. So that's actually straightforward, and we were able to show that by tuning those polarizability parameters, we're able to get much better results. So in this case, for lithium and graphite, the C6 parameter should be 0, in fact, if you want to be closest to the QMC data. So a little quick summary of this work. So we learned a lot about the DFT schemes, and we learned about the importance of capturing the charge transfer. So what did we do based on these results? Well, one thing we didn't do was go off and do lots of DFT-based molecular dynamics. No. What we actually did was go a method higher. We built a reactive classical force field with Adrie van Duyn, ReactFF for this system, so we can actually do many orders of magnitudes more in scale. And in future, we can think of actually skipping the DFT entirely. I see in future that we'll generate all the reference data we need to fit these potentials in the QMC and then go straight to the higher method, skipping the DFT. Obviously for simple-ish systems where there's not a huge number of calculations needed. So I'm slightly over time here. Let me just give some conclusions on the Monte Carlo. So we've learned that you can apply the current methods to transition metal elements successfully, although a lot of care is still needed. So this is something that's improving, but one can't blindly go and apply these methods. Availability of forces and improved optimization in the solid state is desirable, even if it's not absolutely essential. So we can work our way around currently, but clearly it'll be better if we have fully optimized trial wave functions. And I'd also point about when you set up a study to give a lot of thought into extracting useful knowledge from the simulation, because we actually learned a lot more, I would say, from the lithium and graphite studies than we did from the cuprate studies, at least as presented, because we're able to go in, analyze the charge density, and then inform some of our other modeling. So give thought about what you're going to do with these numbers you're computing. And that's all I have for this talk, so thank you for your attention, and I'll be happy to take any questions. David.
I want to make a remark about the van der Waals because this is something that might be a little confusing. Van der Waals interactions are included in the Slater-Jastrow wave function only if you have the correct long-range part in the Jastrow. If you use a short-range Jastrow, you don't have a van der Waals in the variational wave function. I mean, there's a one-to-one correspondence between the energy you're looking for and the term wave function that I showed with that finding cast formula. So, like two graphene sheets, then you're looking at an interaction between one plane and another plane. You need to determine your Jastrow, which goes from one plane to the other plane. It's very simple. And of course, you might say, well, diffusion Monte Carlo is going to fix that up, but you're starting from a disadvantage if you try to pick up everything with diffusion Monte Carlo. It's better to understand that you can put it in your Jastrow.
Yep. So I agree. And there's something also to be careful about. If you make the distances very large, even if you have the long-range behavior in the Jastrow, in practice, you're asking your electrons or your walkers to potentially walk a long way to resolve this small interaction. So you have to be very careful with the statistics and the analysis to make sure that you're resolving that interaction correctly. You can have long equilibration times quite easily there.
Yes. So have you ever done any QMC calculation on model system? I mean, model Hamiltonian, for example, the three-band model and like honeycomb models. Do you have it in your QMC pack?
Okay. So there were two questions there, which is, have I ever done any calculations of, for example, the three-band Hubbard model, and are Hubbard models in QMC pack? So I have done, and I work with people who focus essentially full-time on lattice Hamiltonians, the Hubbard model, and its generalizations. QMC pack is really a real space QMC code, however, and you want to use different Monte Carlo techniques to, for example, access finite temperatures. So you might be asking different questions. Now, the form of the Hamiltonian is very flexible, and you might even be able to set this up, but primarily we're focusing on real space calculations with quantum Monte Carlo. Of course, we would like to make the connection to go through. This is why I spoke about learning from the density matrices, for example, from these systems, because then one could check that the properties of the zero temperature many-body wave function that we have when all the atoms are present is well reproduced by your generalized Hubbard model, for example. That seems to be very important. So a few groups are actually working in that direction.